analyze. So I would need to say, get me the submission for Edward for assignment 4 and get me the 4th version of that submission. And that gets me to a particular data of that particular submission and that date as well, but blah, right? So that gets me the actual data of that submission, right? So in this scenario, the discriminator is the version, but the strong entity sets are student and assignment. So in case of student, that is the strong entity set, its primary key is username, that is also the only key. So that is the table for student. In case of assignment, again, the primary key is the name of the assignment, that is the primary key, plus the other junk that we have for the assignment as well. In case of submission though, that is related to 2 of those tables. That means that we need both username and the assignment name for us to be able to actually have directed a particular submission. That means that all 3 of those, even though both of those are many-to-one relationships, right? But we still need username, short name, and version to be the primary key for this particular submission. So that is why we need username, the assignment name, and the version for this submission. And I want you guys to tell me now, this ER diagram, does this ER diagram allow group submissions? That is, can multiple students submit the same homework? Yes or no? Edward says no. Is Edward correct? Can I, as a student, join with other students and submit a single project file, which is what we actually want for the final project, right? That the thing that we want is every group will submit a single project. Can we do that in this ER diagram? So if Blackboard is designed like this, which it is, if Blackboard is designed like this, can we submit for group projects? Apart from just telling me no, also tell me why. Yes, Edward. Only one student and one homework, many versions of that. Exactly, because student and assignment are one-to-one relationships with a many relationship with submission. Exactly, Edward. That is the point, right? Because we have designed our database like this, we cannot have group submissions. You are correct. Okay. So any questions up to now about this thing, about these diagrams? So also imagine that somebody has given you this diagram, right? Somebody has given you a formal definition of this diagram or some version of this diagram. Will you be able to convert this diagram into its corresponding SQL code? Right, we need to be able to convert this diagram into its corresponding definition code. Sadly, we will not have a homework that converts this diagram to a SQL code, but I actually had a homework like that, but forget about that. But essentially, we should be able to convert a diagram into its corresponding SQL code, right? Okay. So now we have two other things that we need to actually consider. Two other things that ER diagrams allow, but normal SQL code, at least standardized SQL code, does not. The first thing is composite attributes. So composite attributes are sort of like structures, right? Data structures that contain multiple variables into a single variable. So how do I convert that into its corresponding SQL diagram or SQL code? Let me add to that in the sense that many database vendors actually do allow composite attributes, right? But MySQL, Oracle, I think Oracle does, but I definitely know that MySQL does not. But essentially, how do we convert this? If we are converting it into MySQL, how do we convert a composite attribute into its corresponding SQL code? So a composite attribute might look something like this. That is, an address can have multiple different attributes, right? So it has a street value, it has a city value, it has a state value, it has a zip code value, right? And each of those attributes can have their own domains, right? Street and city could be varchars, zip code could be a normal character length code, and all of those things. State could be a 2-character code, what have you, right? So if we want to convert this into its corresponding SQL code, customer ID and name, so for customer ID, it still is a primary key, name is a normal attribute. And if we want to convert this composite attribute about address into these 4 corresponding addresses, relational algebra does not allow composite attributes. So basically we would have all the individual attributes as our attributes as well. Right? So that is how we convert composite attributes into its corresponding relational model. Okay. Now we have multi-valued attributes. So multi-valued attributes are usually quite useful in terms of, let's say a particular user can have multiple phone numbers, or a particular user can have multiple email addresses. So if you are a member of the Discord server or Reddit or Gmail or what have you, everything you do is already connected to a single email address. So we can infer from Discord and from Reddit and from blah, blah, blah social networking sites that the email ID is a primary key, right? They do not allow multiple email IDs for any particular user. But you can imagine a more lax website that can allow multiple email IDs for a particular user, multiple phone numbers for a particular user, and so on, right? So in that sort of situation, is where multi-valued attributes come in, right? So multi-valued attributes are essentially attributes that can have multiple values or an array of values for a particular attribute. That is an array of phone numbers or an array of addresses and so on, right? So imagine that we have an array of addresses that is usually represented using these curly brackets that we have. So if that is the case, we can sort of break this table down into separate components, right? We can say that customer ID and name is one component, that are all the components that we have here. And we can also break it down into another table that is customer addresses, where customer ID, street, city, state, zip code, all of those things together make up the primary keys, but those are basically values that allow many to many relationships, right? So multiple customers can stay in one address. Multiple addresses can be owned by a single customer. That also applies to, let's say, email addresses as well. A single customer can have multiple email addresses. One single email address can also be held by multiple customers. I know that that is a weird thing to think about nowadays, but one single email address can sort of be held by multiple customers. If you think about, let's say that you have your group email addresses, right? Your EECS group mail. When I send an email to group mail that is EECS, every student in that group gets that particular mail, right? That means that every student in the EECS department is a member of that particular email ID. And that is how that particular database is designed. Does that make sense? And obviously, I can have multiple email IDs, which I obviously do, and you guys, I'm sure, do as well, right? Wichita.edu is not your first email ID, right? Okay. So yes, I guess that's it for ER diagrams. The next thing that we will do basically is we will be skipping over lecture number 17 that talks a bit more about schemas and equivalent schemas and how we combine all of those things. I would suggest that you guys go through those slides and let me know if you have any questions regarding that. But mainly today we will start our discussion on something called normal forms. I don't know how far we will go with this, but essentially we will talk something about we will talk a bit about normal forms. Again, this is not part of your exam, and this is again not part of your homeworks as well, which is already done. But essentially, this is something that we should actually have some basic knowledge about. Okay, so before I talk about normal forms, let's go back to lecture number 16. And we said that we have these ER diagrams that we can sort of design and then convert them into their corresponding relational schema, right? We have a diagram. So initially we just talked about relational algebra stuff and relational schema stuff. Then we talked about this diagram stuff that we can sort of add on multiple constraints such as many to many, one to many, partial constraints, and so on, and basically convert that into its corresponding relational schema. The next thing that we would like to talk about is a bit more abstract, that is, given a particular data set, right? Given that we have an entire data set of a bank, let's say that we have the accounts and the customer names and the addresses, the email IDs, the balances, the loans. Let's say that everything together is in a single table. That is a highly inefficient table, right? That is just a data dump. We would like to convert this particular large dump into corresponding separate tables so that we can organize everything better, right? So how do we organize this entire data dump into a corresponding set of tables for a particular database? So the next thing that we will talk about is essentially something called normal forms that mathematically and formally defines how we can represent a particular data dump into its corresponding separate tables, right? And mainly it looks into certain things. The first thing that it looks into is that a particular representation must be complete. That means that all of the information that we have in this data dump, right? We would like to have that into separate tables, but that also means that we would like to have those separate tables, when combined together, create the entire information as we had originally, right? The second thing that we want is that when we are dividing this data into multiple tables, we really do not want redundant information in those tables. We would like to remove as much redundancy as possible from those tables, but we would also like to break it down into smaller segments so that it is consumed more easily, right? So normal forms basically allows us to formally define what a database would look like. And it also says that a good pattern for a database schema should follow this sort of set of normal forms. And it also says that it also allows us basically to prove, as in PROVE, prove whether a particular key should be a primary key or not. Okay, so it gives you certain, basically it's quite easy. It might sound weird, but it essentially says that if a particular set of constraints follow these rules, then this is a primary key. And if my table follows these rules as well, if my primary key follows these rules as well, then that is a primary key as well. So that is how it proves that this is a particular primary key, or this should be a primary key or not. Right. So the main advantage of normal forms is that, and almost all databases use a normal form called a Boyce